finally we have a radius also, and here whatever we are observing here, that is taken as a dead zone, because which we are keeping 0, means here that is a part of whatever the deformation is there, it is along BC. So, the stress along direction BB means, already we have seen earlier that the stress along BB to the, in comparison to the sigma y, or you can say upon sigma y, that is given by phi upon phi minus 1, or finally this is di minus d final to the power 2 into the phi minus 1 and minus 1. And here what is the phi? Again I am repeating it here, that this one is nothing but 1 plus mu upon tan alpha. So, we have assumed that one, we have taken this one, that is 1 plus mu upon tan alpha, we have taken equal to the phi, and in respect to that we have derived our expression. Here the alpha already we have taken as 45 degree. So, the tan 45, that is equal to 1. In this way our final expression would be here for the value of phi. Now, we are going to discuss about the frictional forces during extrusion process, means the material is moving from left to right, means whatever the arrow has been shown to you. So, it is having a directional motion here. So, whatever the force is there, the force will act opposite to the motion of the flow of the material, and finally we can say that here we have the d initial is here at the cross section of a BB, and total length that was earlier we have taken as a L, and after that the deformations start. So, whatever be the frictional force is there, that has been taken as a K, and sigma x by AA, it is the interface of our ram and the material. So, here we can take as a axial equilibrium. In that region we can write that sigma x at AA multiply by pi by 4 di square, that is equal to sigma x at BB at that boundary, then you can say that pi by 4 di square, because here the diameter is similar one, plus whatever be the pi d, means pi di is the total circumference multiply by the length we have taken into the consideration, multiply by the yield strength or K, that is equal to the K mu p. So, it would be equal to, this expression would be there for the entry zone before BB. So, finally, from here we can say that our F, that is equal to the pi by 4 di square sigma x at BB plus pi by 3 under root of this one into di L upon L into sigma y. So, this one is a total force that is acting at BB, or the total force. Now, we have to find the workload from the energy consideration. So, now we have to find the workload from energy consideration. So, what we have discussed, we will take this one through the energy conservation later on, means after this one, but before that we have taken the forces, whatever the material is given to you that has been under the space is squeezed by the back force, and after that we have taken the small element and we resolve the forces along the x direction and y direction, and finally we concluded that the force and finally the power that is required, that is depending upon the exit velocity and the force at the exit end or initial one. Means if we are taking the initial, then we have to apply the force, initial area or the velocity, or the as earlier we have taken the force at the exit side, the area also at the exit side. Now, we are going to consider the energy concept for the extrusion one. So, this one is a workload for the energy consideration. Here we are assuming that everything is a similar one as we have done earlier, that the shear yield stress is K. Here shear yield stress is K, and the axial velocity at BB means initial cross section that is equal to the VB, which is same for the rim velocity, and this one is also equal to the whatever the ram velocity is there. So, the rate of energy input to the conical work zone across the section BB, we have to take care for that one. Rate of energy input to the conical working zone. Across BB, this would be equal to our sigma x at BB multiply by, you can say, pi by 4 d initial square into velocity of B or velocity of ram. The frictional loss means here we are taking the power at the surface of the element would be equal to our K. So, here we have to take that mu P, that is equal to K, means shear yield stress. For that, whatever be the frictional power is there for frictional power loss, that would be equal to our this K mu P, that pi d root 2 dr under root 2 into velocity. And already we are aware that the conservation of material accordingly we can say that whatever the velocity is there, multiply by pi by 4 d square, this one is equal to whatever the VB pi by 4 di square. So, this diameter at everywhere may be related to our initial diameter or the ram diameter. So, using this we can say that this the whatever the power loss, frictional power loss is there, this power loss is equal to our pi K di square VB dr by r. So, if we are integrating it in the conical working zone, so in conical working zone, so the expression, we had a expression earlier, now we are integrating it. For the material in working zone. In working zone, that is conical one. So, we have the total power loss, frictional power loss, that would be equal to pi k di square velocity of at B and logarithmic di upon df. Or this may be equal to our pi by root 3 sigma y di square Vb log of di upon d final. So, we shall determine now the rate of energy expenditure in the plastic deformation process. For that, the deformation process in working zone means work done per unit volume. Work done